name is Katerina Galitskaya, and this is the 6th and final tutorial in my series on antenna simulations in Nullspace. In the previous episode, we simulated a 4-element antenna array installed on a 10-meter telecom tower and looked how the structure affected performance. In this final episode, we'll take it one step further by adding a second array on the tower. We'll explore how beam steering in both arrays influence coupling and overall radiated performance of the systems, and also see how Nullspace handles this kind of complex install multi-array scenarios. So let's get started. We start by opening a new file, empty file, and our journal. In this project, we basically need to add one more antenna array, and not to do any more like complex 3D modeling. We already simplified our tower structure in the previous episode, so here you can see that as in the previous episode, we imported the tower, we cleaned some surfaces and deleted some features, and so we can just run this journal file and see how it creates the two antenna arrays. The most, I would say, complicated thing here was to actually place antennas on the tower so they in the right position that they wanted, right? So I copy pasted basically one of the arrays. Here we can see our array for elements. 4 elements with the radome, and then the tower itself with the poles, and then I have the second array on the opposite pole. So the goal of this simulation now is to run this model in a full wave solver. So that is very impressive already by itself, that we can run this kind of big model, 2 arrays on a 10-meter tower in full wave solver. And what is interesting for me in this simulation is to see how this antenna affect each other. So basically coupling between them, that's one interesting thing, because as you know, we usually don't have only one antenna hanging on the tower. All the sites now in the cities, if you look outside of your window and see some telecom towers, they usually have a lot of antennas on them, right? So in this scenario, we at least see if the coupling between our antennas is low enough that it will not affect each other. And also we can see while steering if the coupling changes, if it becomes worse or better, and also maybe a radiation pattern changes because of the presence of another antenna. So that's why we kind of do this kind of simulation, and it's very impressive for me, and I think very useful to be able to run this kind of simulation in a full wave solver. So after I modeled this, so I have my model, right? I have my two arrays on the tower and the mesh. Again, we discussed the mesh last time in details about the mesh of the tower and so, but again, the mesh done on kind of separately on some small features here. So I can scroll down to the meshing. I have here Telecom tower meshing, and I basically used my mesh variable that I created before here, depended on my wavelength, and I mesh with it. And then as we discussed in the last episode, we can plot this here, quality of the mesh. We can plot it and see if there is any problems and maybe mesh that particular area better. But I know that this model is meshed good now, so I can go straight forward to the simulation. And in the simulation there is nothing new here. It's pretty much the same as with one array. On the Telecom tower, we again use this compress solver to speed up the simulation. And this is very helpful, of course, because you can imagine how big this this is electrically large problem. And I, for example, do this all on my regular laptop. And if you can imagine that you can run this kind of electrically large problem on a regular laptop in full wave solver, I didn't think that was possible. But this model with the two arrays, right? Arrays with the radom on and everything, and on the tower, it took me like 10 hours, I think. So it simulated overnight on my laptop, like just regular laptop. I think it's very impressive. And yeah, so we just do some far field simulation as usual. And let's go to the post-processing, because that is the most interesting part. We want to see results. So what we do different in this case is that we have, of course, more ports, right? We don't only have S parameter matrix for one array, but we also have in that S parameter matrix second array, right? So we need to kind of spread it, like we need to separate it, and then we need to also understand like what kind of coupling. So S2 and S1, 2, we need to kind of extract from that S parameter matrix. So this is one thing that we need to do, and then another is to assign complex weights, because we want to do beamforming. If you remember from our tutorial on beamforming, we want to assign phase and we want to assign amplitude to each port. So this is what is happening here. And then we again, here I set up my phase shift, right? So first we will see the result for no phase shift, so bore side, both antennas bore side. Then we will change the phase shift and also run the post-processing one more time and see how it goes. So then I plot my coupling versus frequency, and then I do kind of for gain as well. And for gain is also, it's important that I want to excite. I need to know which port I want to excite, right? I know that from first to fourth port is my first array, and then from fifth to eighth port is my second array. So I need to kind of here assign, excite these ports. If I want to switch off one array, I can just assign here like that's there is no excitation, right? But in this case I want to have my both antennas excited. So then I do the same as we've done before a lot of times. I plot some indexes to get good cuts, right, and plots. And then I do also some maximum gain, and I plot all of that. The new thing here is that I also plot coupling versus frequency, but otherwise the plots are kind of similar. It's gain versus frequency, and as well I want to have polar cuts. I want to have my elevation cut, azimuth cut, and then also 3D cut. So let's look at results for our bore side simulation. So we only have now our antennas. As you can see here in elevation, it's very convenient to see that they both excited and radiate like bore side, right? To see with the zero shift. And here we have this kind of interesting pattern. That's two distinguished radiation patterns kind of on both sides. And coupling versus frequency, this is the new thing. So we have here in our I plotted S21 and S12, and essentially we all know that this is kind of the same thing. It should be equal, but that's why I plotted it, because I want to know that my simulation is correct. And if it's equal, then at least I can see that, okay, that part went right. So here we can see that it's equal, and I have around 40 dB coupling between arrays for this bore side case, and I think that's very good coupling, like 40 dB, minus 40 dB, and we also can see a very very interesting looking 3D pattern. It's always interesting to look at 3D pattern. We have a lot of here like side lobes and so, and two of the main lobes kind of looks like a butterfly or something. So let's just change and steer so that one array will steer on so 10 degrees up above horizon, right? And then another array will steer down. And also interested to see what happens in this case, right? And we can see here that actually the coupling changed and it's now lower. So this is good. And we can see our radiation pattern as well. So one array is steering down here around 10 degrees, and another array is steering up, also around 10 degrees. And this is very interesting. So we can conclude that when the beams are kind of not in the same position and steering in kind of different directions, then we have a bit better coupling, like around 45 or like 50 dB. So this is good to know. And we also can look at a very interesting shaped 3D radiation pattern and see that, yeah, I mean, this is very interesting looking. But that's basically what our system radiates now. So from that, our system that consists of two antenna arrays. So that was very interesting for me, this kind of simulation, and I'm also very happy that I could simulate it in full wave solver to run this whole system with a 10-meter tower and so, and to get these results, to have this study done with the beamforming, how beamforming affect coupling on the installed antennas array right on the tower. So this was very interesting for me. I really enjoyed this series, and as you remember, we went through like a lot of different experiences in this series. We started from very, very simple single antenna element, and then now in the end we simulated two antenna arrays with the radome on a 10-meter telecom tower. I think this series was very helpful. At least it was very interesting for me, and I hope that you liked it as well. Have a good day. Bye bye.